Hello, everyone, and welcome to the first lecture for AMAT 611, Basic Functional Analysis. So I will start basically from scratch. I know at least the PhD students have probably seen everything I'm going to do already. And if the two master's students have seen what I'm doing already, then they should let me know. Please let me know, and I will go much faster. I definitely do not want to bore everyone. I do want everyone to get something out of this course. So, okay, so really really in some sense the whole course is going to be more or less based on studying normed vector spaces. So, and we've all probably seen normed vector spaces. So for this course, we're always going to deal with vector spaces either over the real numbers or the complex numbers. Usually it's going to be the complex numbers, but occasionally it'll be over the real numbers. So X is a vector space over the reals or complex numbers. So what is a norm? Well, let's say we have a function that takes X and spits out non-negative numbers. Okay, so we're normed. Sorry about that. Hit the wrong button. So a normed vector space is just a pair, a vector space, and this function here satisfying the following three conditions. So first, apply this function to X. If you get 0, that implies X equals 0. So here little x isn't big X. So I'll always try to put kind of bars here to denote our vector space. And no bars denotes an element of our vector space. Okay. 2, we have the triangle inequality for X and Y and big X. Now the following is true. And third, well, we can pull out scalars. So if alpha is a scalar, so if we're, if it's a real number, if we're dealing with vector spaces over real numbers, or it's a complex number if we're dealing with vector spaces over the complex numbers. Okay, so right, for any scalar alpha and any x and big X, well, we just can pull out alpha. Okay, so if all three of these are true, then we call this function a norm. All right. Okay. And I should also mention in this course, X is either going to be a vector space of sequences or functions, or X is going to be a vector space of linear maps between sequences and functions. And I'm being a little redundant because, of course, a sequence really is just a function whose domain is a subset of integers. So possibly the integers themselves. So, but anyway, so for example, if we take definitely, the simplest example, just set of all n tuples of complex numbers. Well, there's obviously a lot of norms we can give this, or we could do Rn. In general, for p strictly between 1 and infinity, we could give it the p norm. Let me call this LP rather than p here. So, well, I mean, obviously, we know what this is. So you just take the modulus of zj raised to the p, sum it up, bring it to the 1 over p. So, yeah, this is pretty trivially a norm. The only non-trivial thing is checking the triangle inequality 2 here. And that's, you've probably seen, it's just the discrete version of Minkowski's inequality. I'm not going to prove it because it's not a very good use of time, but 1 and 3 are pretty much trivial. Okay. Alternatively, another norm would be just the L infinity norm. And that's just the maximum of each one of these elements here from 1 to n. All right. Yeah, more examples that we've probably all dealt with before is little LP, which is just all sequences. Doesn't have to be indexed by the positive integers, but so it's all sequences of complex numbers where this sum here is finite. Okay. And the norm. So this is for strictly p between 1 and infinity. I should say here, right, p is between 1 and infinity. I said it, but might as well write it down. Right. Yeah, so the little LP norm is basically the same thing. So sum j equals 1 to infinity, cj to the p over p. Again, this is pretty trivially a norm. Minkowski's inequality says the triangle inequality is true. And when p is infinity, the little L infinity norm is just the maximum of all the zj's. And little L infinity is basically the same thing, except the maximum of the zj's is finite. Okay. One last example. So for homework, I'll talk about, when I talk about completions, I'll talk about the example of the Sobolev space. I'll probably introduce in the homework the concept of a weak derivative. We won't really do much with it because there's really no time to do PDEs. But I guess if there's time in the end, I'll maybe do something a little more advanced that people are interested in, whatever that might be. We'll see. But anyway, so one last, straightforward example that's quite important for the purposes of this course. Well, just looking at continuous functions on 0 to 1, or really this could be any compact Hausdorff space. And so, yeah, this is just all continuous functions on 0 to 1, complex valued, that are continuous. So f is continuous on 0 to 1. And you give it the obvious soup norm. Infinity here. It's just going to be the max. And because f is continuous, the maximum exists. Right? And this is pretty trivial that this is a norm. Okay, so one non-trivial aspect of all this I want to get into that the book seems to kind of glance over, which I think it's worth at least spending a little bit of time on, is the idea of a norm versus a semi-norm. So in practice, you often have 2 and 3, but 1 isn't quite true. And in those instances, that's okay. You can kind of force 1 to be true in some sense. Okay, so right, so I'm going to define a semi-norm as a pair x and this function here, which remember takes in x and spits out non-negative numbers. And it's a pair x and this function here where 2 and 3 are true. So in other words, we're not necessarily assuming 1 is true. And you should be able to think of a very natural example of a semi-normed vector space. And that's just basically Lebesgue spaces. So let's say P is bigger or equal to 1 and not infinity. So let's say X is, you don't really have to just deal with functions on the real line, but I mean, yeah, really, you can replace this with any measure space, but whatever. So let's say we're just dealing with complex valued functions that are measurable, where this here is finite. So I'm not calling this LP because it's really not LP. As I'll make more precise later. Okay, so we can define a semi-norm on X, the LP semi-norm, in the obvious way. Just take the modulus of f of x, raise it to the p, integrate 1 over p. And again, this works for any measure space whatsoever. So Minkowski's inequality tells you that the triangle inequality is true, and you can trivially pull out scalars. Okay. Right. So right. So in this case here, we have that obviously this equals 0 implies that f is not the zero element of the vector space big X, but that f, all it tells us, of course, is that f is 0 almost everywhere on R. Okay. Okay, so the question is, how do you make, and you should know the answer to this because this was done in 510A or whenever you took measure theory. So how do we make this? And you do basically the same thing when p equals infinity. So how do you make this a normed space? And I'm doing this because I want to go over a general procedure to basically cook up a normed vector space from a semi-normed vector space. So when I say space, I always mean vector space. And I should mention a lot of times, instead of writing X and the norm for a normed space. I'll just say, let big X be a normed space, and implicit is a norm. You know. So, okay, well, so we define an equivalence relation. So this is equivalence here. So we define an equivalence relation as follows. We say F is equivalent to G, and I'm going to write it like this because for any norm space we can, basically do this. So in 510A, you said F is equivalent to G if F equals G almost everywhere. Well, of course, you know, and you proved in 510A that this is equivalent to F equals G almost everywhere on R, or whatever measure space you're dealing with. If you're dealing with an arbitrary measure space, F equals G almost everywhere with respect to your measure. Okay. All right, so right, what you next do is you just define the equivalence class. So if F is in script X, you define the equivalence class as you always define equivalence classes. Just a set of all elements in your vector space that's equivalent to your given F. Okay. So of course, being a little bit redundant, but this is set of all G, where G equals F almost everywhere on R. Okay. So you define your kind of new vector space as just a set of all equivalence classes. And you define the norm, and it will be a legitimate norm in the fairly obvious way. So when I write this with two dots, it's a definition. I'm defining this norm here for F in big X to be, well, just the LP norm of F. Okay. Right. And so, if you don't really remember your 510A all that well, this is maybe is a little murky because, well, what if we pick, what if we basically pick another representative of this equivalence class, and we use this definition on that representative? Does that give us the same answer? Does that spit out the same number? And the answer is yes. So, right, and that's pretty trivial. So G in this equivalence class is the same thing as saying G equals F almost everywhere. And that means, well, these LP norms are obviously the same. And that means, by definition, this definition here, the definition of this norm here, is independent of the representative chosen for this equivalence class. Remember that in general, when we have equivalence relation, we have two equivalence classes. Maybe I should put it in a slightly different way. We have two equivalence classes are equal precisely when one is equivalent to the other. Okay. Right, so we're checking if what I said previous is not clear. What we're doing here is we are checking. So this is if and only if. It's kind of messy here, but right, we're checking that if we have the same class, if we have two different ways of representing the same class, the class generated by G, the class generated by F, if they're equal, then do we get the same norm? Is this norm defined on these classes? Does it make sense? Is it well defined? Okay, so yeah, we just proved that it is. Okay, so right, let me end off this video with basically abstracting this procedure in general. So, and I don't want to really dwell on this too much, but basically whenever you have an actual semi-norm, you always go through this procedure, usually without really saying all that much, to get a norm. So we have a proposition that I'm going to prove in a second. So let X be a semi-norm. Semi-normed vector space. Okay. So if I define, and for lack of anything really better to call it, let's call it X. I don't know. Let's say X tilde. Whatever. So if X tilde is a set of all equivalence classes generated by each element X, and remember, just like we did before, if it's not clear, we're saying X is equivalent to Y by definition if X minus Y, the norm is 0. Right, so, right, if we define this new vector space in the following way, then we can define a norm on X in the obvious way. Okay. So note here that first of all, we really should give maybe make explicit what the algebraic structure is. We're saying this is a vector space, so we got to be able to add things and do scalar multiplication. Well, it's really not much to that. And we will actually, in general, talk about quotient quotient spaces later on. But yeah, just because this pops up so naturally with LP spaces, I think it's worthwhile to just get this out of the way immediately. Right, so if X is in your vector space big X, then you define alpha times the class X just in an obvious way. And you add up classes, well, in the obvious way also. So there's really not much to the vector space structure for x tilde. I mean, you should prove, particularly here, if there's any doubt, that this is well defined. That, you know, if x is equivalent to x prime, y is equivalent to y prime, then you know, the class x plus y is the same as the class x prime plus y prime. This is in, you know, you should check that this definition is independent of the representatives of x and y for the classes. All right. So before I prove this, or rather, just to make the proof a little shorter, I need the following lemma, which is, you've all seen this, but still, just, make sure we're all on the same page. I'll just state it and prove it. So it's just a reverse triangle inequality. And that states that for any so here X is a semi-normed vector space. Usually this is stated for a normed space, but you know, all it really uses is the triangle inequality. So this is perfectly fine for a semi-normed space. So if X and Y are two elements in my semi-normed vector space X, then we have the following, which says in particular that norms themselves, or semi-norms, are continuous functions. Okay, so yeah. Okay, so the proof is quite easy, and I claim that it's enough to show that minus the norm of x minus y, and even though it's a semi-norm we're dealing with, it's just easier and quicker to say norm. So it's, yeah, we want to prove that the norm of x minus the norm of y is sandwiched between minus the norm of x minus y and the norm of x minus y, because this will imply is actually equivalent to exactly the reverse triangle inequality. The absolute value of the norm of x minus the norm of y is less than or equal to norm of x minus y. Okay, so in general, when you have a quantity b that's bigger or equal to 0, a non-negative quantity b, and you have a real number a that's sandwiched between b and minus b, okay. So it's not really part of the proof, but yeah, so you should recall from basic analysis that whenever you have a situation like this, again, b is non-negative, this is equivalent to the absolute value of a is less than or equal to b. So here a is just absolute value of x minus, sorry, norm of x minus the norm of y. Okay. All right, so right, so let's prove this. And really, this is just two easy applications of the triangle inequality. All right, so to get the first half here, which I'll put in red, we do the following. Right, and yeah, and in a lot of my research, I end up having to use kind of variations of this kind of triangle inequality argument. So it's good to get this kind of idea branded into your head. All right, so if I want this, I'm going to add and subtract y. and then use the, minus and plus. And I'm going to use the triangle inequality. Okay. So this is going to be norm of x minus y plus norm of y. And I just simply bring the norm of y over to the left-hand side. And that gives me norm of x minus norm of y is going to be less than or equal to the norm of x minus y. Okay, so really all we're going to do is switch x and y to get the other half, which I will denote in blue. Right? So now I want to prove this kind of half here. Go back to black. Or really, I'll just go over exactly what I'm going to do. Just play the same game, but swapping the roles. So this is going to be the same thing as y minus x plus x. Use triangle inequality. By property 3, the norm of any element is the norm of minus that element. That's pretty trivial. So this is the same thing as norm of x minus y, and I'll use that fact throughout the course without really mention. Right, so what do we want? We want norm of x minus y on the left-hand side. So I'm going to take the norm of x minus y, subtract it from both sides, and I'm going to bring over the norm of y. And that's exactly what I wanted, the other half of my inequality right here. All right, and that well, that takes care of the proof. Right? So like I said, it's a pretty easy proof. Okay. So the proof of the proposition is as follows. And before I say anything else about the proof, right, so just note that there's a well-defined zero element in my vector space x tilde, and that's just simply, well, it's the obvious thing. So this is going to be, you can just check this trivially. This is the zero element of x tilde. Okay, so not a deep observation, but anyway. Okay, so right, what I want to first prove is that you know, this norm on x tilde is well defined. Okay. Right, so if x is equivalent to y, I need to show that the norm of x is the norm of y. Okay. Well, how do I do that? Well, use the triangle, reverse triangle inequality. Well, by definition, x is equivalent to y when the norm of x minus y is 0. Okay. And that's, well, equivalent to, in particular, implies that the norm of x by definition is, well, the norm of the class generated by x is by definition the norm of x. That's going to be equal to the norm of y by this here. Okay. And again, this is the definition of the norm of the class generated by y. Okay. Right, so this is independent of the representation picked. Right? If the class of x is equal to the class generated, if the class generated by x is equal to the class generated by y, which is equivalent to this here, then this spits out the same number. Okay. All right, so now we just need to check all three of the conditions, and that's pretty much trivial. So in particular, well, right, so by definition, this is going to be the norm of x. So first of all, let's say 0. Let's assume this is 0 here. Okay. So I can do something kind of silly here, which is just subtract the 0. I mean, it's not so silly. But, right, so by definition, we have the norm of x minus 0 is 0. So by definition, that means x is equivalent to 0. And that means, well, that we really do have the 0 class. Okay? So on x tilde, on the vector space of all these equivalence classes, the norm of the class, the norm of any class being 0 means the class is the 0 class. All right. So not much there. 2, well, really 2 and 3 are kind of trivial. I'll just do 2 very quickly. Not much to this because you know, as I mentioned, how to add classes together. So particular, this is by definition, well, inside the norm, we don't know it's a norm yet, but whatever. Right, so we know how to add 2 classes up. We know by definition what this is. This is just the norm of x plus y. I mean, this is a seminorm, but like I said, I'll just still call it a norm. Now I use triangle inequality. And by definition, this is the norm of this class here and the norm of the class generated by y. And 3, there's just not a whole lot to this. I'll just do it very quickly. So by definition, this is going to be alpha times x is, alpha is a scalar. This is the class generated by alpha times x. And again, by definition, this is the norm of alpha x, which we know is the absolute value of alpha times the norm of x. And that finishes up the proof. So later on, we'll talk more generally about quotient spaces. They're quite interesting and useful. But just because this appears so naturally when dealing with probability theory, Lebesgue integration, et cetera, it's worthwhile, I think, to kind of go over this procedure. All right, so what I'm going to talk about next is completeness. And as many of you probably already know, most theorems in functional analysis require completeness. even in applied math and machine learning, you really want complete vector spaces. You deal with reproducing kernel Hilbert spaces, meaning a complete inner product space. So yeah, and if I'm going way too slow, again, please let me know. I don't want to waste people's time. But all right, so long, take care, until next time.